This is a video about Newton's second law of motion, aimed at those studying GCSE Physics or GCSE Combined Science. If you're taking the AQA syllabus, then this is in paper 2 in the forces topic. In this video, we're going to define Newton's second law of motion and then use that law to calculate the force required to accelerate an object and to work out what the acceleration will be if we know what the size of the force is. We're going to define something called inertial mass and then estimate the speed, acceleration and force used by everyday road transport. In a previous video, we looked at Newton's first law, which tells us that when the resultant or overall force acting on an object is zero, acceleration will be zero. So that means that motion is constant. If it's stationary, it stays stationary, and if it's moving, it will carry on moving in exactly the same way. It can't speed up, it can't slow down, and it can't change direction. Newton's second law of motion carries on directly from the first law of motion, and it describes what will happen if a resultant force that isn't zero is acting on an object. Newton's second law actually tells us that the acceleration of an object is proportional to the resultant force acting on the object. So that means that if I double the force, I'll double the acceleration. And it's inversely proportional to the mass of an object. So that means that if I have an object that's twice as heavy, the same force will cause it to accelerate only half as much. We can express this mathematically using the formula force is mass times acceleration. As with all of your physics equations, it's vital that you know what the standard international units for each quantity are. If you were to accidentally write a mass in grams instead of in kilograms when you use this calculation, then your answer would be out by a factor of 1,000. So, force is measured in newtons, mass is measured in kilograms, and acceleration is measured in meters per second squared. And for shorthand, that's a capital N, a little kg, and a meter/s squared. Remember, acceleration is a vector, which means that it has both a magnitude and a direction. So although in everyday life when we say acceleration we mean getting faster, in physics it's entirely possible for it to mean getting slower. And if that's the case, then we'll show it with a negative number. Let's practice substituting some numbers into this formula and doing some calculations. In the first question, we're asked what force is required to accelerate a 5 kilogram box by 2 meters per second. Now, sometimes in the exams they will be extra kind to you and they might say a box with a mass of 5 kilograms and an acceleration of 2 meters per second squared. But even if they don't do that, I know which number is which because I've got those units on the end. So wherever I see kilograms, it must be a mass, and wherever I see meters per second squared, it must be an acceleration. So I take the 5 from the 5 kilograms and I put it where mass would be. And I take the 2 from the 2 meters per second squared and I put it where acceleration would be. And I don't need to do anything with that 2. Sometimes I see people trying to square it because they see the square in the units, but the acceleration is just 2. So now that I've got 5 in place of mass and 2 in place of acceleration, I multiply them together to get a force of 10 newtons. Hopefully that's quite straightforward to you, so pause the video and try and do the next 4 questions on your own. Assuming you've managed to substitute into that equation correctly, you should have come up with answers of 210 newtons, 4.8 newtons, 16,000 newtons, and 0.0005 newtons. You probably noticed that on the previous slide, for the last question in particular, it seems kind of silly that I'm giving my mass in kilograms. Why on earth would I measure the mass of a snail in kilos? Well, the reason I'm doing it is because in order to get the right answer out of the equation, I need the mass that I put in to be in kilograms. But let's be realistic here. If I've got something that weighs less than a kilo, chances are that I'm going to write that mass in grams instead. So for some of these questions, you're going to need to convert your mass. And if we're trying to go from grams to kilograms, you divide by 1,000. So 5,000 grams is going to be 5 kilograms. Pause the video and now have a go at these 5 questions, but this time watch out for masses that aren't in kilograms already because you'll need to convert them first. So my very first question is one where I need to convert 300 grams divided by 1,000 will be 0.3 kilograms. 0.3 kilograms multiplied by an acceleration of 3 meters per second squared takes a force of 0.9 newtons. My 60 kilogram woman doesn't need converting because that's already in kilograms, so 60 times by 2 is 120 newtons. But my 200 gram book does need converting, so remember 200 divided by 1,000 would be 0.2, and 0.2 multiplied by 7 is 1.4 newtons. My 8,000 gram racing bike could also be written as 8 kilograms, and 8 multiplied by 6 is 48 newtons. And finally, my 10 gram snail in kilograms weighs 0.01 kilograms, and that multiplied by 0.2 is a force of 0.002 newtons. Now that we can do these mathematical calculations, what does this actually tell us? Well, a number of things that, to be honest, are kind of intuitive anyway. It just proves them mathematically. The first one is that it takes a bigger force to accelerate a heavier object. Well, that seems kind of obvious. If I want to accelerate a pen and I want to accelerate a car, of course the car takes a bigger force to accelerate it. The second thing is that it takes a bigger force to create a larger acceleration. So again, that just seems kind of intuitive. If I want to gently increase my speed, or I want to suddenly speed up very quickly, suddenly speeding up very quickly is going to require a bigger force. The third thing it tells us is that it takes the same amount of force to speed something up as it does to slow it down. And the fourth thing is that if I've got a force of a set size, then that same force applied to a lighter object will cause it to accelerate more than if I applied that force to a heavier object, which again is just kind of intuitive. If I push my pen and I push my car with the same force, of course the pen is going to accelerate more. We've already used this equation to calculate force, but now let's use it to calculate acceleration. You should be practicing with all of your GCSE physics calculations, rearranging them to make something different the subject. Here, acceleration is currently being multiplied by mass, and the way you get rid of something that's currently multiplying is to divide it. And whatever I do to the right side of the equation, I have to do to the left side. So to rearrange this, I'm going to divide both sides by mass. And now I have force divided by mass is acceleration. So to work out the acceleration, I'm going to take the force in newtons and divide it by the mass in kilograms. You're now going to use this rearranged equation to work out what the acceleration of these 5 objects are. Remember before you start to check that the mass in each instance is in kilograms, and if it isn't, you need to convert it by dividing by 1,000. Pause the video and write down an acceleration for each object. The 300 gram box has a mass of 0.3 kilograms, so 24 divided by 0.3 gives an acceleration of 8 meters per second squared. The 60 kilograms don't need converting, they're already in kilograms, so 24 divided by 60 is 0.4 meters per second squared. The 200 gram book is 0.2 kilograms, so that gives us an acceleration of 120, and the 8 kilogram racing bike will have an acceleration of 3 meters per second squared. Finally, our teeny tiny snail, if we put a whole force of 24 newtons on it, is going to have a massive acceleration of 24,000 meters per second squared. Having rearranged this equation once, we can use the same technique to arrange it to make mass the subject. So mass is currently multiplied by acceleration. To get rid of that multiplied by acceleration, we need to divide by acceleration, and whatever we do to the right side, we do to the left. So we're left with an equation of force divided by acceleration is mass. There's actually a special name for this, which you need to know if you're taking the higher tier. Inertial mass is a measure of how difficult it is to change the velocity of an object, and it can be calculated by the ratio of force over acceleration, which is exactly what we've just done. Pause the video again and calculate what the inertial mass of each object is based on the fact that when subjected to a 60 Newton force, it accelerates by the following amounts. An object which responds to a 60 Newton resultant force by accelerating by 5 meters per second squared must have an inertial mass of 60 divided by 5, which is 12 kilograms. If it accelerates by 2 meters per second squared, the inertial mass must be 30 kilograms, and if it accelerates by 60 meters per second squared, it must have an inertial mass of 1 kilogram. If it accelerates by 0.8 meters per second squared, the inertial mass is 75 kilograms, and if it accelerates by 0.12 meters per second squared, the inertial mass is 500 kilograms. Finally, for this video, there's a slightly odd statement that's crept into the GCSE Combined Science and Physics specifications by AQA, and it says that you're expected to be able to estimate the speed, accelerations and forces involved in large accelerations for everyday road transport. Now, note that it says estimate, not calculate, so this suggests that they're not necessarily going to give you the exact numbers. So it's helpful if you've already got some kind of ideas of order of scale in your head. One thing I think is quite useful to know is that 1 mile an hour is about the same as 0.45 meters per second. And that's useful because it means you can convert your normal speed limits of 30 and 70 into 13.4 metres a second and 31.3 metres a second, which means that they're actually in the format that we need them to be to use them in calculations here. It's also helpful if you know that an average family car probably weighs about 1,000 kilograms, and lorries in Britain have to be below about, I think it's 44 tonnes, so you can estimate that a lorry maybe has a mass of 40,000 kilograms. And you'll notice that throughout this slide I've used a funny kind of wiggle sign called a tilde, and this basically means approximately equal to, so it's a good sign to use when we're talking about estimating. So let's say that a normal family car with a mass of 1,000 kilograms accelerates from a non-motorway road to the motorway in 10 seconds, and we're asked to determine the size of the force that is required to accelerate that car. Well, the first thing I need to know is how big the acceleration is. So going from 13.4 to 31.3 metres a second is a velocity change of 17.9 metres a second. And to work out acceleration, I do that change in velocity divided by the time it took, which in this instance was 10 seconds. So 17.9 divided by 10 gives me 1.79 metres per second squared. Now I can use force as mass times acceleration to work out the force, which will be 1,000 kilograms multiplied by 1.79 metres per second squared, which gives me a force of 1,790 newtons. I hope that was a useful introduction to Newton's second law of motion. Thank you very much for watching, and if you did find it useful, don't forget to like the video and press the subscribe button below so that you don't miss out on more GCSE Physics videos coming soon.